Okay, so it's my pleasure to introduce Ben Altman. He's Senior Research Analyst at RSSB. He's been at RSSB for 11 years, and 5 of those he's been working on adhesion-related topics. He's currently the Industry Group Manager for the Adhesion Research Group, which I also sit on. So I know that Ben really knows his stuff when it comes to adhesion. So I think tonight's talk will be really fascinating. If we can all give Ben a round of applause, and Ben, the floor is yours.
Thanks everyone for having me, much appreciated. So just to introduce myself before we get going onto the presentation today, I'm going to give a brief introduction on the Adhesion Research Group, the ARG. So as Toby has just alluded to, this is a group that was established 13 years ago. Its ultimate aim is to basically enhance industry and academics' knowledge of the fundamental science and engineering behind wheel rail adhesion, but also related topics as well. So it's not simply looking at it from a scientific point of view. It has its informal links to the old Adhesion Working Group. That's basically where it stemmed from, and various other topics that it touches upon as well will include things such as professional driving policies to do with adhesion, and then anything to do with wrong side track circuit failures due to contamination as well. So it's not purely just adhesion, but it is obviously clearly focused on that. And a key part of this group is all about trying to make sure we get a systematic view of the issue, as well as a systematic view of how can we kind of solve the issue as well. It is facilitated by the Rail Safety Standards Board, so I'm currently responsible for managing the group. I've been involved about 5 or 6 years with it. It's currently got 55 members, and they're from various backgrounds, predominantly engineering backgrounds, unsurprisingly, but there are quite a few operational people there as well. One thing I do plead actually is we're very open to getting any new members, or even guests for that matter. So please feel free after the talk to approach me if you want to join or at least attend a couple of meetings, and I'm more than happy to send some invites your way. Normally meet 6 times a year, usually have hybrid meetings. We're going to be resuming hybrid meetings in the next meeting on 10th of December, just because we recently moved office at RSSB. We act as sponsor for the Adhesion Research Challenge Programme, the ADHERE programme. So this is a programme which is all about trying to, again, strategically tackle adhesion. We're talking not just from, the fundamental science point of view. We're talking about the train elements. We're talking about railhead cleaning, talking about driving policies, and forecasting adhesion as well. So it's trying to be as comprehensive as possible about trying to tackle that. And as part of that, what we try to do is make sure that we encourage the take up of findings as much as possible, because clearly at the end of the day there's a lot of good effort, a lot of money put into these research projects. The last thing we want is for them to sit virtually on the bookshelf. So we engage with various groups in addition to obviously our own groups such as the Seasonal Challenge Steering Group, Seasonal Challenge Communications Group, Vehicle Track System Interface Committee, and so on, to try to make sure that these research projects, recommendations and so on are likely to be taken up. Another thing we do, in addition to kind of proposing and endorsing research, is trying to follow what's being done across the world. I must emphasize there really is a significant amount of stuff that's being done across the world. One of the tasks I've got every 3 months or so is to look across various countries, what activities are being undertaken. There is a significant amount of stuff, particularly in the academic field, but it's not limited to just academic stuff, clearly not. It's a lot of commercial things and so on is being done as well. There's particularly a lot of stuff from UK and China. Hands down, they are the 2 countries that have the most amount of stuff, no question. But then afterwards, you then have a lot of other countries that are doing things, Czech Republic, Italy. Unsurprisingly, like with a lot of industries and topics, you'll end up with particular people or particular organizations who dominate it. You'll often see the same names and same organizations come up. That's quite common. But ultimately, the UK and China, I would say, are probably the two countries with the most amount of activities. And as part of that, we do try to encourage international presentations to our groups, even things that we're not directly involved with. We're just trying to enhance knowledge and make sure we're obviously, not duplicating stuff. So that's just a brief introduction on the group, and please feel free afterwards to kind of approach me on that. So the first proper part of this presentation, I'm going to give a kind of a relatively high level overview on wheel rail contamination, which obviously is the name of the presentation today. Before I do that, I'd just like to start with a very quick quiz. So this quote we have here, is anyone in the room, anyone online, does anyone want to guess what year they think that this quote comes from? Any volunteers? 1822. Okay, so the answer is 1822. So this is over 200 years old. It's from a guy called Nicholas Wood from the Newcastle magazine. It was a magazine, I think, focused on engineering solutions and so on back in the day, and all about the issue of steel wheels and steel rails. So clearly, pretty much wheel well adhesion has been an issue since the dawn of rail. To many, it's unsurprising, but it was obviously quite enlightening when I managed to find this quote, just again proving that this is not a new thing by any means. So I thought I'd start out with that. So basically, the first thing to say, the wheel well contact patch is incredibly small. It's approximately 1 or so centimeters squared, so it's basically the equivalent of a 5p coin. So the ability for trains to accelerate and brake is dependent on the available adhesion within the contact patch. So a significant advantage of the contact patch is low rolling resistance, which enables rail to be energy efficient. However, the small size of the contact patch means that even small amounts of contamination can potentially result in low adhesion. And it should be emphasized that this is not an issue that is limited to GB. Absolutely not. It is pretty much an issue across the world. Obviously, to what extent differs depending on different circumstances and so on. But certainly I have bags of evidence to show that it is indeed very much an issue, not just in Europe, it's in Japan, or certainly parts of Japan, parts of China. So China, for example, the main issue they tend to have is with high-speed rail, because they have the largest high-speed rail network in the world. And unsurprisingly, when you have so much of a network, that's potentially where you're going to encounter more issues there. The image we have here, which is courtesy Crown copyright, obviously, of the raid. This is from the Salisbury incident that happened in October 21. I'll be talking about that later. Another thing I'd really like to emphasize here is that the wheel well interface, the reason it's such a complicated thing when it comes to adhesion is an open tribological system. It means it's basically impacted by a significant amount of factors. You're talking about, obviously, the physical factors, the chemical factors, the biological factors. It's everything together. And it's the fact that adhesion is not as constant. It's not a static thing that you say, oh, okay, we've got an issue over 5 kilometers. It is exactly the same issue. And then it just goes, but no, it's basically, it obviously changes, but it's very much a highly transient and highly localized issue. It's a thing that can appear within minutes to hours and can be within meters to tens of meters to hundreds of meters. We're not normally talking about kilometers to kilometers. That can happen, but it's usually relatively localized. And that's what makes controlling it, trying to understand it, trying to monitor it and manage it very, very challenging. So, why is it such an issue? Well, it can cause SPADs, signals passed at danger. It can cause station overruns, buffer stop collisions, train collisions, derailments. But it is not just an adhesion issue. So contamination, and this is deliberately why I've named the talk as it is, wheel well contamination can and does quite often cause wrong side track circuit failures. And again, I'll be talking on that shortly. But it's effectively where you have the signaling system thinking that there isn't a train when in fact there is one there, which can be very serious, obviously. Okay, sorry about this. So now I'm going to start talking about the contaminants themselves. So there are a large number of contaminants. It's not just the obvious ones, which I'll get onto shortly, but I will start with the most obvious one. So crushed leaf film is probably one of the most well-known third-body contaminants for a very good reason, and that can have a significant impact, but usually not by itself. It's usually the interaction of the various contaminants that have a thing, and I'll get onto that later. And again, not just adhesion is also very much a significant issue with wrong side track circuit failures. So the image we have on the right, this is a piece of work that University of Sheffield did for us a couple of years ago, which I'll be talking about later. This is from a national data set they got from Network Rail over a 10-year period, so 2012 to 2022. And the leaf contamination was categorized as 60% of all wrong side track circuit failures. Unsurprisingly, the vast majority of those were over October to November. And if you're interested, the other 15% was rust, followed by sand or sandite, and then grease and oil. And the 19% is basically non-contaminated stuff. So the vast majority of wrong side track circuit failures tend to be related to contamination. I've got now another quiz. Here we are. So there are an estimated 13 million trees within 60 meters of the GB main line. If you're wondering, 2018 Network Rail undertook an aerial survey by helicopter to record the number of trees within the main line. How many of those 13 million trees do you think are on Network Rail's estates, at least as of 2018? Any guesses? 6?
9.
3? 9? Okay. The answer is 6. So the estimates I found online and in various literature can differ significantly, but a mature tree, and obviously that depends very much on the type of tree and where the tree is and so on, can have anywhere between about 10,000 to 200,000 leaves. So unsurprisingly, when you figure out the amount of trees that are within 60 meters, so there's 6 million, but actually it's 13 million within 60 meters, you're effectively literally talking about hundreds of billions of leaves every autumn that are falling near or on the railway. So again, this is just something to kind of think about for context. What I have here is basically an outline of the main components of plant cell walls. This is where it's going to get slightly more technical. So this is specifically to do with dry brown leaves. So they basically comprise of cell walls containing a thing called polyphenols and polysaccharides. The polyphenols largely comprise of lignins, tannins, whilst the polysaccharides contain pectins, hemicellulose, and cellulose. We had some research undertaken a few years ago by University of York that identified that the composition of these components varied quite minimally between different dry leaf species. However, when the crushed leaf samples were transitioning to leaf film on the railhead, there was a significant increase in the polyphenols and a decrease in the polysaccharides. And I'll get on to the transitioning of leaves to crushed leaves shortly as well. Okay, so about this. So leaf fall or leaf opposition is influenced by quite a lot of factors. So usually deciduous trees, they predominantly shed their leaves in autumn. And this includes air temperature. So a reduction in air temperature, in particular the onset of frost, can have a significant influence on leaf fall. But conversely, warmer temperatures in autumn may potentially prolong leaf fall. Soil moisture. So drought stress potentially can result in early leaf fall. It's something that was seen about 3 years ago. So you might have seen reports about the fake autumn where there was a particularly long summer and then it brought down quite a lot of leaves early on. Something that can happen from time to time. Soil type. So that might have a major influence on the quality and decomposition rates of leaf litters. Wind speed. So increased wind speed may result in an increase in leaf fall, but conversely, calm to light winds are thought to contribute to prolonged leaf fall. Leaf type. So the timing and rate of leaf fall can differ significantly by leaf species. So for example, oak is thought to be one of the last deciduous trees that usually sheds its leaf in the UK. And then there's also a thing called photoperiod, or in other words, the period of the time of the day that a plant is exposed to light. That might be potentially a factor as well. So basically, the less light you get, you're more likely to result in an increased rate of leaf fall. So these are some, not necessarily all, but these are some of the factors that can influence leaf fall. Now, once obviously the leaves start falling, you've then obviously got a wide range of factors that can influence how that builds up on the railhead. And unsurprisingly, tree proximity to the railway is obviously going to be one of the most significant factors. So vegetation management is absolutely critical. I can't stress that. In terms of trying to reduce leaf fall. So, for example, research by University of Huddersfield identified that as few as 5 leaves applied to the rail could result in a consistent black leaf layer over 1.6 meters. It should be noted, however, that contaminant transfer can occur and does occur occasionally miles away from the source. So just because you're, let's say, near a station that's nowhere near a number of trees doesn't necessarily mean you won't result in any issue to do with leaf fall. Railway cuttings is quite a well-known issue, more likely to accumulate a higher number of leaves than embankments or flat grounds. It seemed to be more of a prone thing there. And that was shown, for example, in the Southbury incident when they looked at investigation on that. Tree density. So a low adhesion risk prediction model was developed by University of Sheffield and Chiltern Railways, and density of the trees along the railway was considered for them the key risk parameter responsible for low adhesion. Train aerodynamics. So actually, the shape, or particularly the front end design of trains, can have a significant impact on how leaves get entrapped into the wheel rail interface. And this is particularly problematic with trains fitted with obstacle deflectors. There was 1 or 2 research projects done about 15 years ago that specifically looked at this issue. But to be honest with you, in practical terms, there isn't much we can do from a financial, in terms of an economic point of view on that. Wheel load. So this is absolutely key. It's considered to have a major role in the bonding of leaf layers, and it has a statistical significance on the resulting adhesion levels. So higher wheel loads can result in more bonded leaf layers. It's a very, very key part there in terms of how well does a leaf layer bond. Number of axle passes. So this image here is a piece of work that University of Huddersfield recently did for us. This is on the Harold rig, and basically it's considered to have a significant influence in the build-up, but also the removal of leaf layers. So basically, Huddersfield University found that there was a linear relationship between the number of axle passes and leaf bonding strength. And they found the removal of leaf contamination can occur with approximately 300 axle passes. However, this has to factor axle load, as a higher axle load may reduce the number of passes required to remove leaf contamination from the railhead. And just to say, what we have here from Huddersfield, so this didn't have any added iron oxide, and it was using American oak leaf and small amounts of water. And as you can see basically the amounts of leaf layer that are kind of transitioning from increased to kind of decreased from about 180 axle passes afterwards. Further factors include temperature in the wheel rail contact. So temperatures in the rail contact can vary quite a lot. They're estimated to be usually, if you don't include braking, about 100 to 300 degrees, but can reach about 600 degrees Celsius or higher, especially if you've got flash temperatures during sliding. And it's considered to have a significant factor in the formation of leaf contamination, as well as other contaminant types as well. So the diversity of rail vehicles. So a reduction in rail traffic might result in a narrow running band, resulting potentially in more railhead contamination. In addition to that, an introduction of new rolling stock, if it becomes a dominant rolling stock on that line, could potentially result in a narrow running band as well. I'll be talking about a particular incident that happened a couple of years ago later that the RAB investigated, where this was absolutely a key factor. Leaf hydration. So basically, leaf hydration can impact potentially the stiffness and mass of leaves during and after leaf fall. Wet leaves have a higher likelihood of adhering to other leaves and surfaces, including the railhead. Leaf type. So leaf type and wetting rate were identified to be the most significant factors in influencing leaf layer thickness. So unsurprisingly, that is absolutely a key thing. Wind direction, that might influence the spread and direction of fallen leaves. Unsurprisingly, if you have a particular, wind going over a certain direction, you may potentially end up with a load of leaves going over a particular patch of the railway that might be potentially more prone, particularly, for example, like a cutting. Tread brakes versus disc brakes. So tread brakes, just for context, are predominantly fitted with brake blocks that, when activated, can reduce the buildup of contamination on the wheel rail tread. The vast majority of GB mainline rolling stock have disc brakes, whereas the vast majority of freight wagons and some freight locomotives on the GB mainline have tread brakes. If I'm not mistaken, I think with Transport for London, it's actually a lot of the London Underground still have tread brakes, if I'm not mistaken. And the interesting thing is, it is thought that anecdotally that actually tread brakes do help in terms of reducing contamination, certainly for wrong side track circuit failures. Very marginally, whether it really helps with adhesion as well. There was some analysis back in 2012 that tried to look at data analysis on station overruns, which didn't find much of a difference. But based on experimental tests and so on, certainly from a contamination point of view, in terms of reducing the risk of wrong side track circuit failures, tread brakes are thought to be slightly better. But obviously, disc brakes do absolutely have their own advantages, of course, as well. So surface roughness. So in practical terms, pretty much all solids have a degree of surface roughness. Surface roughness is very much transient in nature. It's not static. It's continuously evolving due to continuous wear and so on. And an increase in surface roughness was identified to decrease electrical resistance and leaf contaminated contact. And then you've got the activation of WSP, so wheel slide protection and sanders. Any activation of this is thought to have a significant influence on the wheel rail interface, whether that's from the train sliding, whether that's to do with sand being deposited under the railhead, but also the combination of that might impact reducing the build-up of leaf heads on the line, where you're having sand particles and grains, you're having axle passes and so on, and slowly you're getting the top leaf layer, for example, starting to break up from that. Now, obviously, I've gone through quite a few things there to do with leaf contamination. Just going to go through some of the other types of contaminants we have. Water, absolutely critical, absolutely critical. So, or rather, how much of it? So this is definitely one of the most important factors, and in many ways, it's how it combines with all the other elements that we have. So, wetting rate. Or in other words, small amounts of water, moisture in the wheel rail contact can form pastes with other contaminants, which can result in ultra-low adhesion. So ultra-low adhesion is basically anything under 0.05 coefficient of friction or something like that. So interesting work that University of Huddersfield did. They found that basically a rainfall rate of about 0.5 millimeter to 2.2 millimeter per hour was likely to contribute to reduced adhesion levels. And in comparison, when they did some experimental testing, they found that a rainfall rate of under 0.5 millimeters per hour might be too dry, whereas a rainfall rate of over 2.2 millimeter per hour might be too wet. So they found that basically wetting rate was the most significant factor in leaf layer bonding strength, and also had a significant input on adhesion. It also identified that leaf layer thickness was the most affected by the interaction between wetting and leaf type. So again, very much key things. Low adhesion often is frequently associated with dew, so small amounts of water droplets and drizzle. Dew usually forms in the morning and evening due to condensation and can accumulate about 0.5 millimeters at night, whereas drizzle is classified as water droplets that are normally smaller than 0.5 millimeters in diameter. So often when you'll see incidents happening, they're not always, but quite often you will see a lot of incidents happening very early in the morning, normally first thing, particularly if you've got engineering trains and so on, or very late at night. Conversely, and I should really emphasize this, heavy rainfall, so anything about 4 millimeters per hour or higher, can soften up third body contaminant layers quite a lot, enabling some of its removals from the passenger trains, so subsequent axle passes. And the concept of using rainy day conditions to improve braking and traction is a technology that's actually focused, a company called WaterTrack, some of you may have heard of, and that's very much what that basically is. That's for kind of passenger trains. Another thing, water evaporation and condensation are very much thought to be key factors in the transient nature of low adhesion. So another thing to kind of think about there. Just get to the next bit. So humidity. So low adhesion is thought to be more likely to occur in high humidity conditions. Relative humidity of about 75% and above was identified to contribute to increase low adhesion. But conversely, a relative humidity of under 40% was comparable to dry circumstances. So what we have really is a combination of high humidity and low temperature, which has been really shown to have a significant impact on causing kind of really low adhesion. So this viscosity. So on this one, this is talking about really the pastes that you get, where you get a mixture of different contaminant types on the wheel rail interface. And they can contain liquids such as water, solids such as iron oxides. It's the viscosity of these third body contaminants that are influenced by factors such as evaporation and temperature. And it's the rheological properties of these pastes that are likely to have quite a large impact on adhesion. Temperature. So we've talked about temperature in the wheel rail contact, particularly to do with braking, but this temperature is more the environmental temperature. So particularly where you get things like melted snow and ice, that can, for example, due to the high temperatures from frictional braking, that can also potentially result in transient low adhesion occurring. So iron oxide. So rust basically is one of the other big three or so kind of contaminants. So there is a large variety of iron oxides that can be found in the railhead. That can, for example, include magnetite and hematite, but there are many others that are found as well. So the formation of oxides is influenced by a variety of factors. That's including the environment, the temperature, the pressure in the wheel rail contact, and so on. And when you combine this with other factors, notably small amounts of water, it can have a significant impact on reducing adhesion, as well as obviously the chemical reaction with the rail and leaves. So University of York identified that there was a significant increase in iron content when you had crushed leaves, so crushed leaves, dried leaf samples, transitioning to fully formed railhead films, where they basically went to a test track, had a kind of a shunter going up and down until it was kind of well embedded in the railhead. They found that basically you had a 115 times increase in iron content in oak species between crushed leaf and fully formed leaf. That's what the graph here is. And also there was quite a large increase in, I think it's copper, I think Cu as well, I think 35 times as well. So quite a large increase. It does depend on the species as well, but as you can see, even with sycamore, there's quite a notable increase in that. Okay. Oh, apologies, just before the other one. Another thing just to say about rust. So over 2012 to 2022, you might remember I was giving that fact about 60% leaf contamination. 15% of that was wrong side track circuit failures due to rust, but that was in the national picture. But on the Wells and Western route, rust contamination accounted for 35% of wrong side track circuit failures. The interesting thing we found with that, though, is actually that unlike leaf contamination, which unsurprisingly is predominantly kind of October, November, a bit in December, rust contamination is generally very consistent throughout the year. You might get a few peaks and troughs, but it's nowhere near the same level that you get kind of with leaf contamination. It's quite a different consistent, to be honest. Oil. So there are actually quite a lot of different oil contaminants that you can find on the railway. Nowhere to the same extent, arguably, as, let's say, leaf contamination, iron oxides, and so on, but it still can be relatively common. That can include things such as hydraulic fluid spillage, friction modifiers, de-icing fluids, diesel spillage, and so on. Both oil and mixed oil water contaminants can reduce adhesion, but based on available information I've managed to find, I believe that you actually get lower adhesion values when you have oil alone. So usually if it's just an oil contamination versus oil and water, you'll usually get lower adhesion values with just oil. Okay, sorry, this. Friction modifiers, so I briefly mentioned this, but I'm going to go to this in a bit more detail now. So there's actually quite a large number of friction modifiers that are available for the railway, and it's used for a number of different circumstances. It's predominantly to manage friction, and this includes traction gels, sand, top of rail lubricants, so those are basically greases and oils, top of rail friction modifiers, so that's water-based products, and top of rail hybrid products. So they're a mixture of water-based and oil-based products. And depending on the product type, these products can be dispensed by train, trackside equipment, or by staff. Two ones I want to particularly focus on. Traction gel. So these are applied to the railhead to increase friction. When they initially dispensed, almost always they will cause an initial drop in adhesion, but that's nearly always then going to be followed by an increase in adhesion compared to dry conditions. The other advantage of the traction gel applicators is, as well as obviously being dispensed by the railhead treatment trains, is that they're likely to be able to remove oxide layers and increase surface roughness as well. And then we have sands. Sands can significantly improve adhesion levels in contamination conditions compared to dry conditions. And as mentioned previously, it can aid in the removal of leaf layers from the railhead. However, sand is an insulator, and excessive sand can create an electrical resistance between the wheel and the rail, impacting track circuit performance. That's exactly why we have standards in place to stipulate what is the maximum amount of sand that can be deposited in the wheel well content. Industrial contaminants. So low adhesion can be caused, it's not super common, but it can be caused by a range of industrial contaminants. That includes, for example, kerosene. So sometimes where you get stations near airports, Luton Airport, for example, very occasionally where you get kerosene in the air mixing with low levels of moisture and so on, you may potentially get incidents, or you may get contamination happening. It's also more to do with actual industrial locations, things like sawdust, coal dust obviously not being as common now, but again, certainly there were historically quite a few reports of that as well. So again, that is definitely an element that can happen. And then you've got everything else, which can be quite diverse, to be honest. So I'll give 2 or 3 very different examples. Rock salt or sodium chloride. That's used to de-ice roads and pavements. It's a bit anecdotal, but as road vehicles pass level crossings, it's thought this contaminant can spread onto the railhead. And there have been a number of experiments that have actually shown how salt can reduce adhesion and can increase oxidation. Completely different example, which has got thankfully nothing to do in this country. So some countries such as Australia and Japan, millipedes, believe it or not, can actually be an issue. So I can give a specific example. 3rd of September 2013, minor collision occurred between two trains in Clarkson, Perth, Australia. So that resulted in 6 injuries. And the incident was strongly suspected to be caused by Portuguese millipedes. They're quite local in that area. It thought that the oils from the dead millipedes basically caused the train to lose traction. A few years later, so 2009, 1.2 miles of track was swarmed by millipedes near Melbourne, causing significant cancellations and delays. So thankfully an issue we don't get here, but it certainly is an issue in some other countries. Another example actually is mud. So again, I'll be honest with you, probably not as much evidence compared to some of the other contaminants I've mentioned here, but mud potentially when subject to moisture could potentially result in low adhesion as well. And in addition to the contaminants mentioned just now, I should also note that there are other non-contaminant factors, such as surface roughness, angle of attack, train speed, and so on, that can have significant influences on adhesion as well. So as you can see, lots of different contaminants, of which there's a lot of interaction between them. It's trying to understand that's where it kind of gets quite challenging. So that was the first main part of this this seminar. The second bit is now I'm going to go through about 3 or so notable incidents and what's kind of the lessons learned in terms of what the Rail Accident Investigation Branch RAIB have kind of looked at. So this image here we have, courtesy of the RAIB, is relating to an incident that happened in Stonegate. 8th of November 2010, passenger train overran Stonegate Station in East Sussex by over 2.4 miles with the emergency brakes continuously applied. In fact, it was actually more than 2.4 miles in total. The train actually, it took the train 3.2 miles to come to a stop after the driver first applied the brakes in brake step 2. What was interesting was that when the RAIB did the investigation, they found that almost certainly there was no sand in the sandhoppers at the leading end of the train. And had sand been present in the sandhoppers, this would have almost certainly enabled the train to stop in a much shorter stopping distance than had occurred. Thankfully, there were no injuries, but there were actually prosecutions because the train was allowed to go out into service when clearly it shouldn't have been. What does this highlight? Well, really 2 main things. The incident highlighted the vital role of sanders in low adhesion conditions, but also how absolutely critical it is in terms of ensuring sandhoppers have sufficient sand ahead of entering service. So that's one thing to think about, just about how long can a train kind of take to stop if they don't have sanders. The next thing I'm going to do, I'm going to play a brief video. Oh, sorry, apologies, I'm looking at the wrong side. Next one I'm doing now is Salisbury. So Salisbury is 31st of October 2021. So this is basically where a passenger train, so it's 1L53, passed a red signal and collided with the side of another passenger train, 1F30. The collision, which took place at Salisbury Tunnel Junction, resulted in the front 2 carriages of 1L53 and the rear 2 carriages of 1F30 to derail. 1 member of railway staff was seriously injured and 13 passengers required hospital treatment as well. It should be stressed actually that potentially far more serious collision could have actually occurred. So had 1L53 actually been travelling in the opposite direction, had 1L53 been travelling about a minute earlier, it probably could have had a head-on collision with another train. And it's not just a head-on collision; it's head-on collision next to the tunnel junction to a tunnel. What the RAIB found was that it was probable that the collision could have been avoided altogether had 1L53 been fitted with double rail rate sanders. And I'll get on to that later in terms of rail rate sanding. So what I'm going to do now is I'm going to play a very short video. It has no sound for everyone, just for information, and then I'll just talk about that now. So let me do that. Go. Right, so 24th of November 2019, 2 road vehicles crossed the Norwich Road level crossing near New Rackheath, Norfolk, in front of the train. The train reached level crossing less than half a second after the second road vehicle was clear, as you can see. What the RAIB investigated actually was that railhead contamination there was a lot of railhead contamination in the immediate vicinity. The narrow band on which the train wheels were running was a consequence of the introduction of new trains, which left the wheel rail interface vulnerable to poor electrical contact. and it resulted in the level crossing equipment to misinterpret the position of the train, and consequently it opened the crossing to road traffic while the train was closely approaching. So as you might remember me mentioning about 5 minutes ago or so, this whole thing about how mixed is the rail traffic? Do you have a new dominant rail fleet being introduced? Very, very important, particularly when it comes to anything to do with track circuit failures. This incident in particular that really drew light to that as being an absolutely key factor there. So those were just 3 kind of incidents I wanted to touch upon, 2 adhesion related, 1 on alongside track circuit failures, and trying to see what we can learn from that. What I'm going to do now, the third part of the seminar, I'm going to be talking about 2 key examples of research that RSSB, with the support of the Adhesion Research Group, has undertaken. Just giving some of the key findings and seeing what is industry kind of doing about that. So the first one is going to be back on track circuit failures. So what are track circuits? Why are they important? So just to give some brief context, track circuits are a type of train detection system that detects the presence or absence of a rail vehicle within a defined section of track. It is absolutely not a new technology. It actually originates from about the 19th century. And what I've done is I've included a high-level schematic on the left, but also I've just shown, for more context, a track circuit cabinet on the right, just to show you what that kind of looks like. I don't think they normally include laptops. The laptop was from our researcher from University of Sheffield who was doing the project for us. So anyway, I thought I'd include that. Sorry about that. So yes, so that's basically just a very brief overview of that. So why is it such an issue? So basically, wheel contamination can potentially electrically insulate trains' wheel from the rail. Basically, the system thinks that there's no train there when there should be. And that's what we normally refer to as a wrong side track circuit failure. Whilst the vast majority of track circuits don't encounter these issues, incidents can result in significant delays, investigation time, and have potential for really serious risk. Previous research that we did about 5 or 6 years ago recommended the replacement of low voltage DC track circuits because they are hands down the most prone to wheel rail contamination. So replacing these with more immune track circuit types or axle counters was considered, a feasible thing to do. Obviously, if there's a budget to do that. This project that I'm going to be talking about now, T1222, that built upon that research. But it then set about how to provide greater insight on for the nearer term on trying to impact the mitigations to wrong-side track circuit failures. Okay, so what did this project do? So this is a piece of work we did with University of Sheffield. It was actually quite a diverse piece of work. It wasn't just a thing where it was looking at 1 or 2 things. It actually looked at various data sources, did various types of testing. So it did a national data analysis from Network Rail's system on looking at wrong-side track circuit failures over 10 years. That includes the diagrams I previously showed with the 60%, 50%, and so on. Had analysis on 6 case study lines, which I'll be talking on slightly more detail shortly. Laboratory testing, track testing, undertaken at Wensleydale Heritage Railway. So that's where some of our Sheffield colleagues are doing preparation in advance of testing. And also, of course, the important thing, production, it actually did 2 good practice guides in terms of trying to mitigate the reduction of wrong side track circuit failures. So 6 case study lines, or nearly full 6 case studies, were selected for their history of wrong side track circuit failures, the mix of locations and track circuit types. It was very much based on engaging with the steering group, seeing where there was an interest, seeing where there was particular problems, trying to focus on that. These are the lines that we looked at. So they are quite well spread out throughout the country, so certainly in different routes. So that will include lines such as Bedford to Bletchley, which, as I'll get into shortly, has actually historically had quite a few issues. And then other ones such as Settle and Carlisle Line, Neasden South, and so on. And what the university did, was there was a list of parameters that they formulated to assess the risk, and that was based on traffic frequency, axle load, traffic diversity, track circuit type, railhead treatment frequency, and tree encroachment. Now, hopefully some of these things will now ring a bell because of what I've been mentioning earlier, things such as axle load, traffic diversity, tree encroachment. A lot of these things were considered to be kind of main elements. And as part of that, what they did was they then looked, I think it was Google Earth, they basically showed that tree proximity to the line was obviously most consequential when it comes to adhesion. So they factored that is likely to be a very similar case with wrong side track circuit failures as well. So they calculated tree encroachment from satellite imagery, I think it was Google Earth, by measuring the area tract not covered by the trees and subtracting this from a nominal area. So this is basically how they kind of did the analysis for the case study lines. I'll be honest with you, I think because it was done manually, there was an intention to do it automatically with AI, but due to timeframes, it didn't. So it was done manually, which can take a bit of time. So from that, they then managed to find quite interesting findings, really. What this did is the risk factor parameters enabled identification of key contributors to this risk. And it's particularly useful where you want to try to see if there's a dominant factor or not. So, for example, in Hull, which is on the top right in green, the track circuit type or vulnerability seems the main issue. Whereas Nottingley west to Shaftholme, so the one in the middle left, the red one, is actually a mix of factors. And actually, it's where you have a mix of factors where you're considered to have an extremely high risk of wrong side track circuit failures. So obviously, it's a problem where you've got one dominant one, but where you've got multiple dominant ones, such as Nottingley West, that's where you really need to kind of really pay attention on that. Okay. Another type of analysis was also undertaken looking at separate data sets. So where they looked at wrong side track circuit failure location data and plotted that, they found two other very interesting things here. So Bedford to Bletchley on the top right, you'll notice you basically have a horizontal clustering, whereas Settle and Carlisle, you have a vertical clustering. What Bletchley to Bedford seems to indicate, so this is the Marston Vale line, is this is before the current, I think the 150s. I think they had the Viva Rail units temporarily for about 2 or 3 years. When they were introduced within about half a year or so, suddenly you see this massive upspike in wrong side track circuit failures throughout the whole line. It's not just in 1 or 2 areas, which very heavily seem to indicate that the rolling stock might have been a key factor. Settle and Carlisle's complete opposite. If you look at this, yes, you get a few things outliers, but the vast majority of incidents are all happening pretty much at exactly the same time over like 5 or 6 years. So again, this was very, very interesting in terms of being able to use this as a kind of analysis on that. So that's the wrong side track circuit failure project. The other initiative that I'll be talking about is actually a number of initiatives that we did. It's all about variable rate standards. So some of you might have heard about this. So 2017, RSSB undertook extensive on-track testing on the Class 387 at RIDC Melton, previously Melton Mowbray. And that was to test various sander configurations. So there were 225 individual test runs that were undertaken and they were analysed. It was then followed by a number of other initiatives. We did an implementation pilot with West Midland Trains on their Class 323, so that was undertaken over 2018, 2019. And the really positive thing on that is that provided very similar results to the on-track testing. So that gave us the confidence that it was, it's not just because it's one particular kind of unit. And what we have here is just a very simple schematic of what a single fixed rate sander is. So basically in green, that's where you have the active sanders in the direction of travel, whereas obviously the double rate sanders, you clearly have 2 of them. Normally it's axle 3 and I think axle 11 if I'm not mistaken, but it depends on the unit type. It depends on the number of units you have as well. So this is one of our infamous graphics, is one of 2 actually. This one is to show you what kind of significant stopping distance you can get. So you have the worst case scenario effectively where you don't have sander working, which is the unstandard, all the way down to DVRS, double rate sanders, single rate sanders, SVRS, and then single fixed rate sanders, which is not the norm usually for most rolling stock on the GB mainline. 2 things to emphasize here. We're not just talking about the stopping distance significantly reducing, we're also talking about the consistency. So if you see from an extreme example, with the unstandard, you're talking between about 530 meters to almost 1,500 meters. DVRS, you're talking 345 to 472. So it's not just the fact that you're significantly reducing distances, you're also significantly reducing consistency, which is absolutely critical. And just for reference, if those are aware, I think it says it here, these tests were undertaken at 55 miles per hour, because I think it was the fastest we were able to do, with an adhesion reference between 0.02 and 0.0245. And that was in brake step 3. So this is on the 387. So before we did the implementation pilot and also afterwards as well, we wanted to understand the use case, because ultimately we knew very much this is going to be the so what. What can the industry do? What will industry want to do as a result of this? And it isn't just simply the case of saying, well, look at these results. do it, we needed to see, well, what are the practical logistical implications of this? So there were 9 classes on the GB mainline that were considered for retrofit. Our suppliers continued working with us, and we were looking at them on each particular basis. And there were actually a lot of factors that had to be considered in terms of upgrading that. So you had to consider things such as space availability underneath the train, the attachment of sand hoppers and sand hose brackets, air supply, electrical supply, sander control signals, and use cases and so on. Obviously, back then, I don't think there were as many battery multiple units as they are now. But certainly where you have a battery multiple unit, yes, it's going to be a bit more challenging because you clearly want to use as much space underneath the train for batteries. So again, maybe that's where a single variable rate sander might potentially be a bit more applicable. But yeah, just to say, there are a lot of factors that have to be considered when you are upgrading a train. It's always clearly easier when you've got a new build because you've got much more flexibility there. But the reality is that by the time you decide to do these things, it's a bit too late usually. So that's again why the ones that have been fitted, it's mostly retrofit. And as ever, there's a lot of standards and documentation that are key in terms of trying to support this journey. So absolutely, one of the key ones is the rail industry standard, RIS GMR T2461 sanding equipment. That was updated to recognise double variate sanders, but also before that, the ability to unsuppress trailing sanders. Again, from a previous research we did, which basically showed how there was significantly more risk if you had a station overrun or a signal pass of danger than a wrong side track circuit failure, particularly when these incidents didn't happen all too often. It also changed the guidance on free car fitment as well, but it didn't change anything on the sand laying rates itself. Key train requirements, I think now version 7 is available quite a while ago, but it was version 6 at the time. That was updated to include a recommendation for new trains to be fitted with variable rate sanders. And also RIS 8040 TOM managing low adhesion, that was also generically, that was more updated to kind of make reference to the work and to adopt a common system approach as well. The analysis they did from a safety risk model showed that if you had a short 6% G braking, DVRS should be able to reduce the risk of low adhesion related SPADs and station overrun significantly. Those are the numbers that used. But I have to emphasize that it's not just, of course, trains. So apart from maybe the core on Thames Link and maybe 1 or 2 other sections I've unintentionally forgotten about, the vast majority on the GB mainline is obviously manually driven. And to realise those operational performance benefits, driving practices are likely to need updating. So sanders are generally, but not entirely, configured to only activate in brake steps 2. It very much depends. Some rolling stock is brake step 1, some it's brake step 3, but usually it's brake step 2 above or equivalent if you've got like an analog controller. And basically WSP, the wheel side protection activation, is needed to call on the sand. So basically, where you have a 3 or 5 car formation, usually those are considered the best to be suitable for DVRS. But if you've got 1 or 2 car formation, you can still have single variable rate sanding, which is it's very effective, not as effective as double rate sanders, but it's seen as a very, very good compromise. And okay, I won't lie, we're a bit biased, but we do think that DVRS is probably one of the most important game changers we've had in terms of making a significant difference in braking in low adhesion condition. And we think that from the evidence we've had from the test tracks and in terms of the driver familiarization runs that we have, we do think that that is one of the biggest changes we've had in terms of making a significant difference. So you're probably wondering, well, what's actually been done? What has actually been done on GB mainline? So Northern trains, the entire Class 323 fleet being fitted with double variate sanders. Southwestern Railway, in fact, there was actually a few articles recently on the news. They had their entire Class 158 and 159s. They were fitted with single variate sanders. And I was lucky enough to attend their test run. That's where the picture comes from at RDC Tuxford back in, I think, February or March. DVRS fitment is being undertaken. Fortunately, there's delays, but it's being undertaken with ScotRail on the Class 170s at the moment. So once the ScotRail is done, there'll be 2 fleets of DVRS and then 2 individual fleets for Southwestern Railway with the new single variable rate sanding. There's obviously other people interested as well, but being transparent with you, this was funded by the Performance Innovation Fund. It wasn't funded by themselves. This is where it gets difficult. It's where it comes to how industry is structured. Where did the costs lie? Where did the benefits lie? Ultimately, the fitment of the variable rate sanders has to date has had to be through funding mechanisms, not through the organisation itself. And that's where it becomes challenging, particularly when it comes to implementation. So that's definitely sort of kind of food for thought, I think. But that's that from me.
So we microphone out. But Ben has kindly offered to take questions. If there are any, I mean, that was really comprehensive. I'm sure there's plenty of food for thought. So, ready? Yeah. Take a question. I think Tim, you had your hand up first. Yep. Go ahead and ask.
Thank you very much. Very interesting. What are the consequences on things like ballast permeability and infilling of continuously pouring ground up sand into it?
I have heard. So this is anecdotal. I must stress this. I don't have any evidence, but I have heard anecdotally it can cause vegetation. It can cause the growth of something. I've heard that if you have too much sand in the ballast, it can potentially cause something. It's obviously
Does it also affect its drainage ability?
It's a good question. I'm not sure. Very good question, but I'm not sure, unfortunately. It's unfortunately one of these realities where the sand has to go somewhere. It normally ends up in the ballast, but it's a very good question. I have heard that it might potentially encourage the growth of something. I'm not sure on the stability of that, but that is a very, very good question.
Yeah, I just worry that it fills up the holes and stops it being such a good drainage medium.
Definitely something to consider. Thank you.
Yeah. Yeah. The next question.
Yeah, thank you for the talk. You said the best results from the double variable rate sanders are occurring in 3 to 4 car formation units. Particularly in the southeast, you get lots of double or even triple formation of trains, and now you have longer formation, single sets. Will you still see the same results in those longer formation trains, or
yes,
will the sheer presence of the number of sanders from each unit?
So the testing,
Question.
the testing that was done was predominantly, it was an REC melter. It was predominantly on a 4-car plus 387. But for about 2 weeks or so, there was testing also with an additional 4-car units. GW were lucky enough to give us that. They were brand new trains at the time. So there was a brief amount of testing that was undertaken on an 8-car formation. And that pretty much confirmed the results. The thing that we have lots of evidence, and this is the general thing, is usually the longer the track formation, the more amount of axle passes you're going to have. You're going to have better conditioning. And the more conditioning you have in terms of the railhead being cleaned from the wheels going over the sand and so on. So usually that's actually a positive thing if you've got more wheel sets and so on. So, but certainly from the amount of testing that we've done, we didn't see any significant differences between the 4-car and the 8-car. And if anything, I would imagine in the real world that actually you're probably going to get better results with long train formations. As you say, things like GTR, so they've got very long trains, formations and so on.
Are there any mechanical methods that railways use to clear up railhead contaminations, like a sort of giant wire brush or giant scrubbing thing?
Yes, actually, funny enough, in this country they even do it here as well. So you have mechanical scrubbers. They're not always, but they are often petrol driven, but they can be battery driven. Normally, if I understand correctly, they are a combination of something. I could be wrong. I think they're not normally in isolation. So you use something. You'd use like a chemical cleaner, like a thing called citrusol. Or
train mounted.
Exactly. It could be train mounted, but it can also be hand mounted, hand operated as well. Historically, I know they've definitely used that in Sweden, possibly Netherlands, and a few other places. How effective is it is somewhat questionable. I've seen evidence suggest it's quite effective, but not for very long. Like it doesn't take too many axle passes, i.e. a few hours, depending on the route and so on, or actually it might not be, it may not last those long. And of course, the problem you've got, especially if it's handheld, is you've got the red zone working, whatever it is, where you've got to take a possession in order to do it. So it absolutely has its own problems, particularly anything to do with how long is it going to take? Given I think even the ones that are driven are very, very slow. We're talking, I don't know, 5 miles per hour, 4 miles per hour. Obviously, if it's handheld, it's going to be particularly slow as well. So you have got limitations. I don't think it's absolutely the most common way of cleaning the railhead, but I have absolutely heard cases even recently that have been done in this country, and I think occasionally abroad as well.
Thank you, Ben. There's a couple of questions in the chat online, so I'm just going to go through some of those. So the first one comes in from Phil Bolton.
Yep.
He asks, given that data suggests that 60% of wrong side track failures is due to leaf contamination and only 5% due to sand.
Yep.
Should there be less focus in standards on limiting the use of sand?
Yeah.
Due to the concern over the impact on track circuits, more focus on encouraging the use of sand to improve braking performance?
Great question. So this is exactly why we had a project T1046 published around 2016, if I remember correctly, that was all about that question. What is the trade-off? What is the trade-off and risk between wrong side track circuit failures and the risk of low adhesion related SPADs, low adhesion station overruns? Now, admittedly, it's a bit of an old project and it's using even older data, but it was very, very telling. I could be wrong on the number. It was something like at the time, the risk of a low adhesion related SPAD or station overrun was considered 170 times higher than the risk of a wrong side track circuit failure. And that was the compelling evidence that basically led to change, originally deviations, and then an actual change, GMRT 2461 standard, to allow the unsuppressing of standards. You had this situation where you had effectively fixed rate standards, but only the first, on axle 3 or whatever, only the first one was allowed to be activated. To our knowledge, pretty much, if not everyone, nearly most or a significant amount of operators in this country have unsuppressed it since then, with very positive feedback. And we think it has made quite a difference. And that's key, because we can't have double variate standards without the unsuppressing. It would have been single variate standards. So again, that absolutely is a very, very good question. And again, it's a thing that gets asked time and time again, that thing about the number. And actually, it's actually really good, because we have recently undertaken some research, some kind of experimental testing on alternatives to sand. Basically, it's not technically not sand, it's traction enhancing materials, but they're more conductive than sand, with about the same stopping distance in terms of braking. So we're hoping that we might do a trial in early 2025 with Northern Trains. We did some very brief tests at RSSB Tuxford. That was the reason we were there. And that was very, very compelling in terms of stuff. But realistically, in the near term, it's probably more to do with where you've got non-electrified lines, because you've obviously got so many different safety risk assessments you have to do. That, well, what's the risks of it, on the further out, for example. So again, it's probably more to do with non-electrified lines, at least in the time being, but we have looked at the capability of that. But yeah, absolutely. It's always this age-old question. Effectively, you've got the signalling community saying one thing, you've got the railway, the train-borne colleagues saying one thing, and obviously there's clearly going to be a risk between the two. But it's very much that's what led to that piece of work. Time very, very conclusive.
Great, thank you. There's a couple more questions in the chat around sand. Seems to be a theme.
Yep.
So first one is around routes where track circuits aren't used for train detection. So is there a possibility of setting sanding rates higher on those routes?
Okay. That's a good question. So I'll be honest, I'm not sure what the rules are in relation to that. You're right that these days there are definitely more axle counters being rolled out over time. And obviously their main advantage is that, unlike like the track circuits in autumn and so on, they're not going to be vulnerable to that kind of thing. But again, I wouldn't know. It's a good question though, but you'd obviously have to do that on a local route by route basis, I would imagine. Yeah.
Okay. And then one was commenting that they've seen some experiments using train-mounted dry ice pellets.
Yep.
So you can get rid of the leaf layer.
Yep.
So with these systems have a benefit in terms of reducing the amount of sand.
So that's predominantly not for braking traction directly. My understanding is it's predominantly to clean the railhead. I see that as two different things. Obviously, it does have the advantage of, indirectly certainly will have the advantage of doing something, but I think it's more to do with actually cleaning the railhead, trying to clean the railhead, rather than braking traction. So I broadly see the technologies as really two things. Those that are probably trying to stop, enable the train itself to stop and aid it with traction. So the likes of variable rate sanding, water track, and so on. Then those that are more to do with cleaning the railhead. Water track's a bit of an oddity because it's predominantly benefiting by helping braking. It's used in conjunction with sanders, so it's to do with braking and sanding. But it also is, it's maybe not as conclusive, but it's thought to have this somewhat of a cleaning effect. Remember the thing I'm talking about, heavy rainfall, and how that's helping kind of, soften up the leaf layers, whatever the contaminants are, the railhead and so on. That's thought to potentially have something, but I think there needs to be more evidence in seeing how useful it is. For comparison, if it helps, water track, if I'm not mistaken, is approximately 7 bar in terms of the pressure. Water jetting on the GB mainline is up to 1,500 bar. They're completely different. The railhead cleaning is for one purpose, it's to clean the railhead. Water track is predominantly braking and traction, but it potentially has a side benefit. But yeah, absolutely aware of Cry-Grip. It's very interesting technology, but I think it's predominantly more for cleaning the railhead.
Yeah, and question. Several.
Yeah, so you talked about vegetation management is kind of the key.
Yeah.
So we've, in the UK, at least got a problem with ash dieback.
Yes.
Which is a massive problem. How do you see that impacting adhesion going forward? And it's not the only dead dying disease.
Yeah.
Issue that we're going to see.
Yeah. So I'll be honest. One thing I'm not so sure about is how ash trees, compared to other species, might be more of an impact. I'm absolutely aware of them being the ash dieback being a particular issue. In fact, funny enough, there was a presentation to an Adhesion Research Group a couple of years ago from something that were rail about it, but I can't recall exactly what was being done or looked at. So apologies, I'm not sure what the answer will be on that one. Apart from the fact, yes, I'm absolutely aware that ash dieback unfortunately is a widespread disease, and yeah, it may not cause more issues with leaf fall and that kind of thing. So yeah.
Yeah, I'm interested. There's a lot of work that's been done over the last 10, 15 years about putting sanders onto multiple units, and obviously evolution of that. But what's the much longer term sort of trend? Has there always been this problem, and actually we're only now sort of finding a solution? So, or has it always been a problem about the way the stocks have changed?
So as you might remember from the quote from the beginning, it's pretty much arguably been always an issue. How does it differ? It depends on a significant amount of factors, depending on what speed you need to go to, what the route's like. Obviously, back in the steam days, for various reasons, you may have not had as much vegetation, but then you had other factors as well. Of course, it's a multifaceted thing. That's what makes it so complicated. More generally, actually, in the last few years, we've been focusing more on freight. There's a lot of things that we're interested to become aware. We didn't realise this as a whole, that actually freight braking, particularly wagons, there have been quite a few issues. Some of you might have known the Rail Accident Investigation Branch, RAIB, has actually issued quite a few reports over the last few years. Pencoid, Petrol Bridge, more recently, I think that was 2022, derailment, and then wagons falling off a bridge. And low adhesion was, in these incidents, low adhesion was either considered to be the key factor, one of the key factors, or certainly a potential contributory thing. To the extent that actually there's now a suite of research projects being undertaken by RSSB with the Wagon Condition Programme, which is part of the freight safety programme and so on, about looking at this issue, the whole thing about freight braking adhesion. Traditionally, we tended to think of low adhesion issues in freight predominantly being a traction thing, particularly where you have freight vehicles slipping to a stand, particularly up incline. That's still an issue. I have evidence, I have plenty of evidence of that. But actually, what seems to be potentially much more of a challenging issue seems to be the braking of the wagons, particularly wheel flats. We get there's some incident, I'm not going to say who it was, but apparently a few weeks ago there was a train of 15 wagons and a locomotive, and all 15 of those wagons had entire wheel flats. Apparently autumn 2024 was one of the most difficult autumns that they had, certainly for that operator, which I won't mention who that is. So certainly for freight, that's the key thing. And actually what's really interesting, there's a really interesting technology that's been rolled out, you might have heard of, called the iWagon. It's by VTG Rail UK, who manufacture wagons. They're also an entity charged maintenance, I think, and Knorr-Bremse, who are a multinational brake expert and so on. And they've been experimenting that around. They've done a trial with about, I think they did or have 9 wagons, split free to different freight flows. I don't have the data to hand, so please don't shoot me if I got the information wrong, but I think they found from the data that effectively you were getting, at least in autumn, wheel lock every 6 miles or so. We're not talking about something that happens every few hundred miles, we're talking about everything every few miles. And that really showed just actually how much of an issue it is. It's kind of really enlightening and showing industry, actually, this is a really big problem. like, actually, we need to do stuff now because we might end up with more serious instances, exactly what we don't want. So certainly in the last few years, we've actually been focusing, we're not shifting because we're still, absolutely, there's a lot of issues with passenger trains that we still need to solve and so on, but freight trains are certainly getting, as they should do, particularly do with braking and so on.
Time for one more question. Yeah, okay, go.
Given we're atom transport for London, I thought this might be an appropriate question. How different are the challenges for deep level tube lines in terms of adhesion compared to, say, the main line?
Yeah. So this is a really good question. So I know it's not Transport for London, but this makes me laugh. So I did a bit of a geeky trip to the Glasgow subway a few years ago. I went to Glasgow for one reason. That was to go to the Glasgow subway. I had special access thanks to a colleague who used to work there. And I asked one of the staff, do you get many low adhesion issues? He looked at me and said, what's low adhesion? So very much it depends. Anecdotally, at least, it seems that unless you've got things like tractional gel applicators that are, or lubricators that are having an excessive amount of stuff, you are highly unlikely, unless you've got very, very small microclimates of, dripping water and so on, you're very, very unlikely to get many issues, if any, in like deep underground. It could be very wrong. But of course, you've then got the outdoor sections. That's, so the Piccadilly line, I'm fully aware, vegetation management, 2016. That's why I'm all the time jumping up and down vegetation management. I know well about Piccadilly line. I know well about all the other instances like that. I think that there are definitely a lot of similarities, but then there's a lot of unique things. I think the amount that in certain sections you have so much more tunnel sections. And of course, the other thing is the ATO. Maybe not every single train necessarily, but you have much more ATO than the GB main line. And particularly when it comes to forecasting and how things like the ACAT, the Adhesion Controllers Assessment thing, very, very different, I think, in regards to that. So I see a lot of differences. The other thing, as I mentioned, but I don't know how much of a huge difference it will be, the wheel treads versus the disc brakes, because of the size of the gauging and that kind of stuff as well. So I see similarities, I also see differences. Very, very interesting though. And I think the new Piccadilly line trains, correct me if I'm wrong, they're going to be fitted with Sanders. Could be the first deep tube levels trains with Sanders. So it can be very interesting how that functions compared to the 1973 stock as well. Look forward to that.
Brilliant. Thank you, Ben. Thanks for sharing all those insights. And I mean, encyclopedic knowledge of some of these adhesion research or adhesion contamination issues. So thank you very much for coming tonight and for sharing all those insights with us, taking us on sort of a tour of all the different factors, some of the history, and what the industry is doing to try and manage what is clearly a long-standing issue, but a very current issue, and we're still feeling the impacts of it, every autumn. So it's clearly something that we need to keep working at. I'm sure yourself, along with the Adhesion Research Group, wider industry, will get a handle on things. So if everyone could show their appreciation in an manner, give a just thank